So this is about some joint work with Hoy and Wen from who's at Ohio State. So just the very general question, of which our question is a particular instance, is we're interested in random analytic functions on the plane, and if you fix a curve, say fix a smooth curve, then we want to understand the distribution of the minimum modulus of the function. So what we have in mind is, so what is the distribution here? So for us, it's, we're thinking about very complicated functions, and so there's an asymptotic parameter, which is the degree. And then we're going to put the curve sort of where all the action is, where most of the zeros are, where the function is order 1. Okay, so and then the second type of question is how you can ask, okay, so you understand the level of the minimum, or local minimizers or the global minimum, but how are the or local minima or global minima, but how about the minimizers? So where these optima are achieved, how are they distributed? So for instance, do they come in clusters where you're more, if you have a very low local minimum, is it likely that most of the others are nearby or kind of far away and independent? Okay, and these sorts of questions have been studied a lot for if you just change min to max, then this is a very big hot topic. Okay, so and then so what our particular instance of this question is, so our function is the catch polynomial. So this is, in our curve is the unit circle. So okay, so we can, our methods apply, and we have a theorem for a general class of trigonometric polynomials. So the methods are pretty robust, but I'll just stick to this for the talk. So this is about the simplest sort of random polynomial you could think of writing down, is just to have, so we have a degree n polynomial, and the coefficients are IID centered standardized variables. It's not too hard to see that the n zeros of this function will kind of cluster very closely to the unit circle. Basically because, if you go out a bit beyond the unit circle, if the modulus of z is a bit, 1 plus epsilon, then the largest degree term is growing exponentially, and it's really hard to cancel back down to get a 0. And similarly, it dominates at the other end for z a bit inside the circle. So most of the action is around the circle, and so that's where our curve is. Okay, we have this sub-Gaussian assumption. Really, in the literature, the most well-studied examples are the Gaussian case and the Rademacher case. The sub-Gaussian assumption is, it's not so important that we have really nice tails. That's sort of not really the mechanism for the minimum modulus. So this problem is actually more about anti-concentration than concentration. But having sub-Gaussian, our proof would work with I think a sufficiently high moment, but it's nice for being able to sort of rule out some bad events, but it's not really that this isn't really crucial that it be precisely sub-Gaussian. Okay, questions about the model? All right, so there's been a lot of work on catch polynomials. And so in the literature on random polynomials, I think it seems to me like most of the papers are about how many real zeros are there. There's just a huge literature on this, and so so much that I just had to cut off at 1980. So before 1980, I think these are the major works on the number of real zeros for catch polynomials. So there was a very influential early paper. It's kind of a fun read, of Bloch and Polya from 32, and then Littlewood and Offord from the 40s, studying the discrete coefficient type case. So plus minus 1 coefficients, or I think Bloch and Polya looked at plus minus 1, 0. And the sort of vague, I think this is the only paper that states any motivation then it kind of took on a life of its own. But because it's intrinsically interesting. But the one motivation that they stated is that you could take these as a model for some for Dirichlet series for things like Legendre symbols or the Liouville function or Möbius function. So these are sequences of plus minus ones and sometimes zeros that for which there are pseudo-randomness heuristics. And so what if you just replace them by IID signs? Then you can sort of model Dirichlet series. And there's some implication between the number of real zeros for these catch type polynomials and for Dirichlet series if you sum out to infinity. Okay, so that was sort of the early motivation. And then for the Gaussian case, this was really sort of where this famous Kac-Rice formula was developed for counting critical points of Gaussian functions. And so Mark Kac famously used this to get a precise asymptotic for the number of real zeros. And then this was extended to more general distributions in some subsequent work. Okay, and that's where I'll stop the review of that. But basically, these are the earliest works that started asking general questions about random polynomials, and it's really taken on a life of its own. But there's more than just how many real zeros are there. So we're looking in the complex plane. And okay, so this is sort of what it looks like. Here I'm just sort of depicting the zeros. So it's not so hard to see that most of the zeros will be at scale roughly order 1/n away from the unit circle. And so there have been a couple of works on this process of zeros. So this question of studying the distribution of zeros, it's closely related to our question about the minimum modulus. So there was a work of Schepp and van der Bey that so you can look at the point process of zeros, and they got the limiting intensity for this point process, from which you can deduce that the empirical measure converges to the uniform measure on the circle. So there's sort of roughly the same number in every sector. And then just last year, there was a nice result of Michelin and Sahasrabudha that looked at the distribution of the closest root, so the distance of the closest root to the circle. And this is much more closely related to what we've done. And there's a similar sort of answer. And it turns out that methods can be applied to, our methods can also be applied to this problem. But so what they did is, so if you have n zeros, and then you want to understand what's, how far is the closest zero to the circle? Well, it's not so hard to, well, as we'll see, there's sort of a lot of independence. Once you're pretty well separated, if you have 2 points that are pretty well separated in the circle, then the polynomial behaves pretty much independently. And so it's like you have n independent chances to get something close to the circle, and so it should be at scale 1/n², this distance. And so then if you just, so this is just a point, this is a point process on the line now. So this is on on the real line. And so here this is just scaling up the rescaled distances from the circle. So you're just sort of collapsing this whole point process onto the real line and scaling up. And once you do this, what they show, so it's a very nice clean result, is that this converges to a Poisson point process of intensity 1/12. So, which looks, it's similar to the result that I'll show you about the min modulus. Okay. So what about the min modulus? Okay, so we're on the circle, so I'll reparameterize. So now it looks like a trigonometric series. So I will normalize it so that at every point t it has variance, unit variance. So this random function is of order 1 with high probability at any particular point. order 1 in probability. And so we just parameterize z by e of theta. So this is just the complex exponential notation. Okay, so we have this random sum of waves of increasing frequency. And we've normalized. And what we're interested in is the minimum modulus, the global minimum modulus of this random function. So this random variable has been studied, and Littlewood, I think it was in the 50s, was the first to ask about the min modulus, as far as I can tell. And so he made a conjecture, which isn't a particularly brave conjecture, just that it should go to 0 with n, so with high probability. Okay, so I think that's very believable. That, you know, if the whole thing is order 1 and you have some nice decoupling, is once you separate them, you should be going to 0 somewhere. Okay, so and that does turn out to be the case. So Kashin was the first to show this, so he got an estimate of the form. So it's at least polylog, inverse polylog. I think it's 1/3. Okay, so it's at most 1 over log n to the 1/3. So this confirms Littlewood's conjecture. But it's really much smaller than that. So Konyagan showed that it can't be much bigger than 1 over n, actually. Okay. And then with Schlag, they showed a lower tail estimate. So it can't be much bigger than 1 over n. But also if, so at scale n, you have this empty concentration estimate. So it's sort of near 0, it has a bounded density, effectively has a bounded density asymptotically after scaling up by n. So these two together suggest that it's at scale, that it is at scale 1 over n. I mean, there's a bit of a gap here, but okay. Is it clear so far? Okay, so all right, so that's where our works come in.
Sorry, Nick, this is Mark. If you have Rademacher coefficients, then you may have a 0 exactly at the unit circle. So the last estimate you wrote should break down for small epsilons.
Yeah, okay, yeah, this is for fixed epsilon.
Okay.
Yeah.
Thank you.
Are you talking about letting epsilon go to 0?
Yeah.
Yeah. Okay. Yeah. That's a good point. Yeah. So this is I guess this is for fixed epsilon. Right. Okay. Yeah. Right. Yeah. Yes. Yeah. That's a good point. Thanks. Okay. Right. Because you have the atoms. Yes. Okay. Yeah. That's right. But okay. But we have big O of epsilon for fixed epsilon. Okay, let's say like this. Okay, so
can I ask one
other question? Yeah.
In average expectation of Mn, is it known how does it behave when n goes to infinity?
The expectation of Mn?
Yes.
Well, I'm about to tell you what the distribution is.
Okay.
Yeah. Right. Yeah. So our results. So together with this other result of Yakir and Zaitouni is that it after scaling up by n, it has a limiting exponential distribution with a rate 2 root pi over 3. So there's this work last year of Yakir and Zaitouni where they studied the Gaussian case and they got this limit. And then Hoy and I proved a universality result that I'll talk about. I'll discuss some elements of this proof too. But so what we show, it's a universality result. It's sort of in the true spirit of a universality result in that we don't get a new proof of this fact here. We just our result is that whatever the answer is for the Gaussian case, it's the same for any sub-Gaussian coefficient distribution. Okay, so there's a comparison. All right. So this is so taken together, we get that the limiting distribution is exponential at scale 1/n. Okay. So, and then I had this question also about the minimizers. And so in the proof, you'll see that the minimizers tend to be pretty spread out. And at those local, well, the local minimizers tend to be pretty spread out, and the field behaves roughly independently there. So actually, if, the proof shows that the point process of local minima, so that's just on the real line, that the levels of the local minima, at scale 1/n, it converges to a Poisson point process of intensity square root pi/3, so without the 2. And then you're just, you have some point process of some intensity, and then you're just looking at what's the distribution of the closest point to some fixed point, in this case 0. So it's a signed process, and so that's the distribution of the closest point of Poisson point process of intensity root pi/3 is going to be exponential with rate 2 root pi/3. Okay. All right, because you can land on either side. Okay, so we'll see that in the proofs. We don't state it as a separate theorem. All right, and then as I mentioned, the sub-Gaussianity assumption is just convenient, just to wave away some bad events. But if you go through the lines of the proof, you can be convinced that a sufficiently high moment would be enough for us. Okay, and maybe one could pursue relaxing that. And there are these, the most well-studied examples are the Gaussian case and the Rademacher case. This proof here is a very Gaussian proof, and our proof is a very Rademacher proof in the sense that the Rademacher case really captures all of the difficulties. So it's kind of like in random matrix theory, where so there was a lot of work on invertibility properties of random matrices, and the Rademacher case is sort of a very clean model that captures what were the essential interesting challenges. Okay, I mean, there are some other, I would say, less interesting, but still maybe interesting directions that depend on further details. But for our result, you really, for the Rademacher case, you need the whole proof. So if you have some regularity, some more regularity, for instance, if you have a bounded density, sort of the more empty concentration you have for the coefficient distributions, you can cut off parts of our proof. But for the Rademacher case, you need the whole thing. Okay. All right. So just before getting into some of the ideas, I'll stay a bit longer at a high level and just mention some parallels, sort of compare and contrast with another popular topic, what's been very popular and active lately, which is to look at the maximum modulus. So for various polynomials, so for catch polynomials or polynomials, you can also include weights that decay with the degree. The maximum modulus was studied in these works. Lately, there's been a whole lot of work on characteristic polynomials. So if you take a random unitary matrix, its characteristic polynomial is a random polynomial. And okay, so the min modulus problem is trivial for these because all the zeros are on the circle. But the max modulus problem is very interesting. And as with catch polynomials, the origin story for why people are studying this, again, is it has roots in number theory. So it's well known that this random polynomial seems to be a great model for this random function, where you take the zeta function high up on the critical axis, and you just look at it on a randomly shifted interval. So an interval of order length order 1. If you pick a uniform random interval at that scale, at a large, so t, capital T is an asymptotic parameter. And in this correspondence, log T is like the dimensional matrix. Then this random function on this interval looks a lot like this one. So what's really well known is that the zeros of this function look a lot like the zeros of this function. So this is this Montgomery-Dyson observation. But what's been appreciated recently is that actually the extremes of this function behave like the extremes of this. So if you look at the global maximum of this and this, those also behave similarly in distribution. All right, so there's been a whole lot of work in the past few years. I won't say all of these names. There's a lot of work lately on it falls into this category of extremes for log correlated fields, and that a lot of the really nice ideas are all kind of borrowing from this very nice argument, this nice work of Bramson in the 70s on branching Brownian motion. Okay, but I won't state any results or explain Bramson's ideas. I just want to sort of highlight some parallels. For the maximum modulus problem, for this characteristic polynomial or for other random polynomials, what you really need is very precise joint large deviations principles. So to get to a high level, you really need to understand the precise upper tail for the field at some fixed number of points. And then there's sort of a competition between that and how many chances you have. So you approximate the circle by a mesh, and then you look at, so you can look at the first and second moments for the number of points where the field reaches a certain level. And Bramson has this nice idea where you sort of do this modified second moment. For us, what we really need for the min modulus, it's rather than LDPs and concentration, it's all about central limit theorems and anti-concentration. And and we use comparison of moments. So we actually look at all moments rather than 1 and 2 point functions. And then there's also sort of a parallel between the considerations that come in where, the most well-studied example that I was mentioning above is the Haar case, so that the matrix is a Haar unitary. But you can also look, so with Ofer Zaitouni, we looked at what if you take the matrix from the Haar measure on a discrete subgroup, the group of permutation matrices. You can again, with some effort, you can see that this Bramson mechanism is still in force, but you get all of these extra arithmetic difficulties. So the field behaves poorly. It behaves differently near roots of unity than it does away from roots of unity. And so you sort of, so we just borrowed some techniques from the circle method to sort of decompose the circle. And you just have to argue separately. And a similar thing happens over here. So for the Gaussian case, everything is smooth, and if the coefficients are complex Gaussian, then it's stationary under rotations, which is similarly true for the characteristic polynomial of the Haar matrix. But for the Rademacher case, we similarly have to be careful near roots of unity. All right. Okay, so that's it for high-level motivation. Now I'll just talk a bit about, I'll spend the remaining time talking about some ideas of the proof. Okay, so, and some of these ideas, so they'll be coming from both papers, Yakir, Zaitouni, and our paper. I mean, this project came out of an AIM meeting, so 3 of us were in a room together where some of these ideas happened, and some went into one paper and some went into the other. All right, so, excuse me. So, okay, so we're going to try and capture the local minimum of this function. or the global minimum. And so, all right, to do anything, we're going to need to discretize to look at it on a finite set. So we just take capital N many points equally spaced in the interval, minus pi to pi. And we'll call those T alpha. And then I'll write I alpha for the interval, so the interval of width 2 pi over n, with T alpha as its midpoint. Okay, so what we're going to try and do is, we need some continuity estimates to reduce consideration to the field at this discrete net of points. So Konjagen and Schlag did this, and so what they, once they reduced to a finite set. So this again, this is their result about the lower tail. Here, yeah. So here I'm mentioning that in their result on the upper bound for the lower tail, they similarly reduced to a discrete set, and they did it's a very careful union bound. Okay, so it's not as simple as just it's capital N times the probability of it happening at any fixed point, because, as I said, it behaves differently depending on how well approximated it is by a rational with small denominator. So they have to sort of categorize points based on Diophantine approximation, and so and that's how they got their result. But that loses constants, and so let me convince you. We want to get the distribution, and just doing a union bound is going to be wasteful. It's not going to be possible with that kind of argument. Just using the values of the field at this set of points. So the reason for this is, okay, so here's a picture. So I have, this is our function on the interval. So this is a random polynomial that maps this line segment into a random curve in the plane. And we're trying to find the closest distance that it achieves to the origin. And so we have this mesh of points. So it's not hard to see. So you can see that the derivative of this function is of order n. And so to see, we need to take capital N large enough so that we can see the function is smooth. If it's too small, if it's smaller than 1 over n, then we'll miss the moments when it shoots in close to the origin. So to capture this moment, we need capital N to be quite a bit larger than little n. Okay, but once you do that, then you can see a union bound is going to be wasteful, because if you're just looking at the probability that one point comes within epsilon over n, well, it carries a whole bunch with it, right? So everything that comes in to scale 1 over n brings a whole, this whole loop of points come with it. So a union bound is going to be too wasteful. So to capture the distribution, we want to somehow, so we'll keep the net very fine, but we want to somehow select a single representative point from this journey close to the origin. So we want to find the best point, the point that's closest to the local min. And what we're going to do for that is incorporate information on the derivatives. So we have a criterion to select this point, which I'll try and explain with this picture. So, okay, so here I've zoomed in on this trajectory. So it's like this particle zooming around in the plane, and here it's come close to the origin. And we have these intervals I alpha, so this is the image of one of those intervals, and this is the midpoint. And we want to select this point. So this one is better than its neighbors, and certainly better than this one over here. And we want a criterion to select that one that's based just on the value, this position, so the value of the polynomial at T alpha, but also its derivative. And so we write L alpha is the linearization of Fn around T alpha. So, okay, so the graph of that is, the image of that is this straight line, this tangent line. And then the criterion for us picking this one is that if you drop a perpendicular from the origin to this straight line, it will meet at some distance away from T alpha, if you look in the preimage. So it will meet at a point that's L alpha evaluated at some perturbation of T alpha. So it's a bit over here. And the criterion is that this lies within the interval, so that it's smaller than pi over n. So basically this is saying, so the criterion is, so we need, we select T alpha if Y alpha is smaller than pi over n, pi over capital N. So, and what that means, that just means that when you drop this perpendicular, it's within these bounds here. So if you were to do this with any other one, so here I just put this one over here just to exaggerate it, but here, you can also linearize here. And if you drop a perpendicular from the origin to that straight line, well, that happens over here on the line, which is very far from the image of T alpha over here. So basically the criterion is that these segments, so at this scale, the curve is almost linear. And so we restrict to an event where the second derivative is under control. So the curve is almost linear, and the criterion is basically that this segment looks at the origin face on, so that this drops and meets this segment. Okay. All right, so that's just the picture of our criterion. So this is how we select the alpha, which gives a local minimum. And really the point is that this criterion involves only the function and its derivative at T alpha. We don't need anything else but that data, the function and its derivative at on our discrete net. Okay. So then here's our point process, which approximates. So we have this point process on R, which will be the scaled approximate local minima. So right, UN. So this is the sum over all alpha. And so we'll take, okay, so we'll call the points X alpha. X alpha is going to be, so I've labeled it over here, the distance we call Z alpha over N. We take it to be a signed distance. So this sort of, the sign of Z alpha tells you whether the local minimum, whether this trajectory passes the origin on the left or the right, but it's not so important. It's just convenient to keep it signed. Okay, so the distance is modulus Z alpha over N, and so so we scale up by N to get an order 1 random variable Z alpha. And so X alpha is Z alpha. So you get a Z alpha for every alpha, but we just want to take that one if Y alpha is smaller than pi over N. Okay. And otherwise, let's just put the point out at infinity. Okay. All right, so this is my point process of scaled approximate local minima at the scale 1 over n. So we've scaled them up. We've got all these Z alphas, but most of them we're not going to see within a bounded distance of the origin, because only a bounded number of them are going to satisfy this. The others we just put away at infinity. Okay. Okay, so this is the point process that we're using, and really all we need to do now is show that this is a Poisson point process of the appropriate intensity. So are there any questions about this picture? Okay. Okay, so the next step I'll explain is what we do after we have some control in the distribution. So we're going to be able to make a comparison with the Gaussian case. And that really just the engine for that is very good control on the characteristic function for the joint distribution of the polynomial and its derivative. But I'm deferring explaining that. So once you have really sharp control on the characteristic function, then you can compare the distributions to the Gaussian. And so how does that help? So we've now reduced the task to showing that our point process of approximate scaled local minimizers converges in distribution to a Poisson point process of root pi over 3. And we'll show this by computing moments. So we fix an arbitrary interval j, and so this is just some integer random variable, and we compute factorial moments. And so you can express this as summing over all of the possible points in the net of the probability that all m of these lie in the interval j. So for each one, the probability is going to be of order 1 over capital N. But after doing the whole sum, you get something of order 1 if j is an order 1. So we claim, so this is what we need to show, is we claim that this converges to root pi over 3 length of j to the m. So that basically says that these points, it's like you're throwing them down at random into this interval, independently of each other. Okay. All right, but you can see now that, so by taking moments, we've reduced it to problems about the joint distribution of the polynomial and its derivative at some fixed number of points. And so now we just need to prove universality for the joint distribution of the polynomial. Okay. So, all right, to show this, well, the intensity you can get just from a Gaussian computation. And this is done in the Yakir Zaitouni paper. So here I'll just, all right, so don't look carefully at this. I'm just saying that, so the probability that a single point lies in J. Okay, so this was the probability that this Z alpha lies in a certain range, but also that Y alpha was smaller than a certain level, pi over N. Okay, and this is just the formula for Z alpha, and this is the formula for Y alpha. So it's just a high school geometry exercise to show that these are the formulas. I mean, it's just in terms of, it's in terms of the linearization. So the closest point that a line, dropping a perpendicular from a line to the origin, you get these expressions. So they're just nice functions of the polynomial and its derivative at T alpha. So we have this sort of event. And, well, it's just an event of this form. So it's the probability. So here we're looking under the Gaussian measure. So it's just the probability that the polynomial and its derivative lie in some domain. So I mean, let's just call this, that where these inequalities are satisfied, we'll just call it the domain that depends on n and j. So this is a compact domain with piecewise smooth boundary. Okay. All right, but I don't want you to worry about the actual formula for this domain. The point is that the boundary is fairly smooth. It does depend on n. So this domain gets worse and worse the larger n is, and that's why we need good quantitative results. But it's just some n-dependent domain. And the Gaussian computation shows that for the Gaussian case, the probability that this vector lies in this domain is well, what we want it to be. And then we just want to carry this over to the general case and also get joint intensities. Okay, so here's the basic comparison result. So, so we want to be able to compare the distribution of the polynomial and its derivative at m different points. And so, I mean, basically, we're just, again, thinking of this as a particle that's whizzing around in the plane. Okay, so thinking about the plane as R2, we can fix smooth functions on R4. So this is phase space, functions of the position and the velocity, and look at time, some collection of times in the interval. Okay, and so these just have to have supports in some bounded, of diameter and polynomial order and polynomial order derivatives, but these can be arbitrary. And assuming that these points are reasonably spread out, so I'm not quantifying this here, but also that they're not too well approximated by rationals of small denominator, then you get a really nice comparison. So then you can compare this product of observables in phase space between the general measure and the Gaussian measure. And basically, you save a factor 1 over root n over the product of Lebesgue integrals of these. Okay. Okay, so this we get as a consequence of our control on the characteristic function. Okay, and then where do we go from there? So that's sort of the black box universality ingredient. And then from there, well, so there's a lemma that, okay, so if these times T1 up to Tm are spread out, let's say well separated, then can take the Gaussian expectation under the product in this expression here. So the Gaussian expectation of this product factorizes. So this is just saying that the particle is behaving independently once the times are sufficiently separated. And again, I'm not making a quantitative, I'm not telling you what I mean by separated. Well, what it really means is by at least n to the -1 plus epsilon. Okay, so at scale 1 over n, obviously it correlates. But as soon as you're a bit further away, then the curve behaves independently. And so you can take, well, and then from this, you see that you can take this expectation under, but it's just a computation. You can compute the covariance matrix for the Gaussian, and then it's just a computation to see that you can take this under the product so that the covariance matrix decouples into a chain of blocks. Okay, so we get this independence. You can see this independence from the Gaussian computation, or just looking at the covariance matrix. And then we have this comparison. This is just for well spread out times. And then finally, we just have that the proposition is that points, so with high probability, times T alpha, where X alpha is in J, are well separated. So we can show that it's unlikely that two nearby points, very nearby points, both send a point into J. Okay, so these three taken together basically finish it off. So, so with high probability, the contributing points are far away from each other. If they're far away from each other, then certainly under the Gaussian measure, they look independent. And so the n point intensity is just the power of the first point intensity. And so you get the Poisson moments, or the Poisson point process moments for the Gaussian case. And then we have this comparison for the general case. Okay. There's one other thing that I haven't said yet, which is what happens on points that are not smooth. This you can handle by a sort of Kuhn-Jagen-Schlag type argument. You can do sort of a more crude union bound to handle the field there. So the really hard part of the proof is to take some quantitative notion of what it means to be smooth and show that you get very good control on the characteristic function. Okay, so in the remaining minutes, I'll describe this. Okay, so just at a high level. So, all right, so for this main proposition, what we want to do is we want to show that this vector, so we pick m times, look at the position and the velocities at those different times. So here I normalize by n so that this is an order 1 quantity. And we want to show that this vector, okay, looking at this as a point in R4M, that this is roughly Gaussian with the appropriate covariance matrix, whatever it is that you compute in the Gaussian case. And okay, so what we want is a central limit theorem, but it needs to be a very strong quantitative central limit theorem because we need this to compare well with the Gaussian at very small scales, because our domain that we're trying to estimate depends very badly on n. So if you want to approximate the volume of this domain, basically you want to approximate it with a union of cubes. And to get a good approximation, the cubes need to be very tiny. Okay. All right, but we don't, this turns out to, I mean, this is not true. Okay, so, and it's, it's related to what Mark pointed out earlier. So if you just look at a single time, if you just look at a single point t, well, so what we want is a strong central limit theorem. So if you look at, say, at t equals 0, well, then you have that, so fn of 0 is 1 over root n plus 1. So the phase goes away there, and you just have a sum of IIDs. Okay, so this converges. So let's just imagine the Rademacher case. So this is real. So this does, we do have a central limit theorem, but this does this at the slowest possible rate. Okay, so this only looks, this distribution only looks Gaussian above scale 1 over root n. Okay. All right, so you do have that guarantee from the Barry-Singh theorem. But apart from that, once you zoom in further, it doesn't look Gaussian anymore. You can see the atoms in the gaps. Okay, and then, at say t equals pi over 2, well, okay, so you can see, all right, well, this will just alternate between real and imaginary. And so it's not hard to see that this will converge to a complex Gaussian. Okay, but again, it's too slow. All right, to get better exponents than 1 over root n, you just need to stay away from those points. But then you can imagine that if you're close to a rational with denominator, if you're very close to something with denominator 1 over q, then you're only going to get some exponent depending on q. But we want to go to arbitrary polynomial scales. Okay, and so this is the criterion basically. So to reach arbitrary small scales, to get really good comparison with the Gaussian and have this measure still look very smooth, here's the smoothness assumption. So basically, this just says that the point ti is not close to a rational with denominator of order n to the delta for some small delta. Okay, so as long as you avoid those by this distance, then these points will be okay. And then we also need them to be spread out. Okay, so they need to be, they can be closer than 1 over n, but not too much closer. Once you have these, then we get really good estimates. Okay, and so how do we get, so once we have those assumptions, then what we want to do, the way we get the comparison, of course, is by looking at characteristic functions. And this is just, this variable is just a random walk. So because if you recall, so these were, Fn is a polynomial with coefficients Cj. So this is just 1 over, okay, I guess it was actually n plus 1. So you can pull out the Cj, and then you just have this vector of characters. And then the derivatives. This isn't one. Okay. And let's just call that Vj. So this is a vector in a 4m dimensional phase space. And so here we have a random walk, and we want to show a very strong central limit theorem for this random walk. Okay, so our random walk is called W, and this is basically the result. So we show that if you look, so if you look at the characteristic function in a ball of any, you can go out to any polynomial order, you get decay in n that's super polynomial. And so, okay, so this is because you can go to arbitrary polynomial order here in frequency space. That means you can look at arbitrary polynomially small scales in position space. Okay. All right, and then showing this. So this is really the core estimate, and this is the technical, the most technical part of the proof. But if you haven't heard of it before, this basically is part of this. So there's this inverse Littlewood-Offord theory, which is a part of additive combinatorics, which basically, the punchline of this theory is that random walks like this, where the steps come from some additive group, so here we have vectors, this will concentrate too much. You'll have a poor small ball estimate if and only if there's some additive structure among the coefficients. So it's like you're walking around on a box of low dimension, or a projection of a box. This generalized arithmetic progression is just a projection of a box. Okay, so this was a big deal. This was very important for this problem of estimating the singularity probability of random matrices, or controlling the quantitative control and the invertibility. In that application, this was a collection of scalars, which was a normal vector for a random hyperplane. And you can show that a normal vector of a random hyperplane is unlikely to have arithmetic structure. For us, our steps are not a random vector in any sense. So this is just a deterministic collection of vectors. But they behave pseudo-randomly, because these points, T1 up to Tm, are, they have this smoothness condition. And so the joint distribution of these characters, say, when you evaluate at these different times, they mix very fastly, very quickly. And so they end up behaving independently. Okay, and we could actually carry this on and get higher derivatives as well. But this is the main technical part of the proof, is to show that this collection of vectors does not have very much additive structure. Okay. All right. So and then all right. So I guess final thing I'll say is okay. So what I mean by in terms of controlling the characteristic function, what I mean by not having an additive structure here is just so if you have some frequency vector, this sequence of steps. So here you're looking at a projection of the steps. If you take an arbitrary projection of the steps, it's not, it has to, it avoids the lattice. So there's no, you can't find a vector in frequency space of some polynomial size, so that when you project the steps in that direction, all of them are roughly on the lattice. Okay. Even showing that it avoids 0 is actually turns out to be pretty non-trivial. And that's just the Gaussian case of anti-concentration. So showing that this avoids the origin, not just the, the lattice is much stronger, but just showing that it avoids the origin is that what that is controlling the smallest singular value of the matrix of steps. And that's precisely what determines the small ball probability for the Gaussian vector, is just the condition number of its covariance matrix. So even showing that it avoids 0 turns out to be pretty non-trivial when these points are only slightly spread. Okay, but we have to go further. We actually have to show it avoids the lattice. All right, so I think I better stop there. So thanks for your attention.